That's it. Get comfortable and fall asleep. Over the next hour, we're going to watch all 10 episodes of Mysterious Cosmic Objects in one sitting, taking you through the true terror and romance of the universe. First, I wish everyone sweet dreams. For a long time, there has been a common misunderstanding about black holes. People imagine a black hole as a giant vacuum cleaner. Once anything enters its gravitational range, it instantly disappears without leaving a trace. But the real process of celestial destruction is far more detailed and terrifying. It never happens all at once. The most deadly weapon of a black hole is tidal gravity. Simply put, the side of an object closer to a black hole experiences far stronger gravity than the side farther away from it. This enormous difference in gravitational force creates a continuous stretching force called tidal force. Once an object reaches a critical distance where the tidal force becomes stronger than the forces holding the object together, its destruction officially begins. Imagine a rocky planet continuously falling toward a black hole. The side of the planet closest to the black hole experiences rapidly increasing gravity and is violently pulled toward the black hole's center. Meanwhile, the far side experiences relatively weaker gravity and continues along its original path. Because the two sides are being pulled with different strengths, the planet can no longer maintain its spherical shape. It slowly begins stretching into an elongated shape. As the distance continues to decrease, the difference in gravity becomes even greater. The planet is stretched from an ellipsoid into a long, thin structure, and its rocky layers begin breaking apart first. Molten rock and magma erupt from inside. As the stretching reaches its limit, the planet finally tears apart, breaking into countless fragments. These fragments do not simply disappear immediately into the black hole. Much of the material begins orbiting the black hole at tremendous speeds, forming a blazing and brilliant accretion disk. The fragments continuously collide, rub against one another, and become compressed. Their temperatures can rise to millions of degrees Celsius, releasing extremely powerful X-rays. Even astronomical telescopes millions of light years away can detect the intense light produced by such a catastrophic event. The remaining elongated streams of material are what scientists call the spaghettification effect. The name comes from the way matter is stretched into long, thin strands resembling spaghetti. Many people wonder, can every black hole produce spaghettification? The answer is no. Whether spaghettification occurs depends largely on the mass of the black hole. For supermassive black holes such as the millions of solar mass black holes found at the centers of galaxies, the situation is very different. For these enormous black holes, the region where tidal forces become truly destructive can lie inside the event horizon. An object could cross the event horizon before experiencing the strongest tidal forces. An outside observer would therefore never be able to see the complete process of its destruction. The spaghettification events we can actually observe mostly come from stellar mass black holes. These black holes typically have masses ranging from a few times to several dozen times the mass of the Sun. For them, the critical tidal force region can exist outside the event horizon, allowing the complete destruction of a star to be observed. Throughout astronomical history, scientists have observed multiple real cases of stars being torn apart by black holes. In a distant galaxy, an ordinary star can accidentally wander into the gravitational influence of a black hole. Its material is ripped apart by tidal forces. Huge amounts of gas form a brilliant accretion disk that continues glowing for months or even years. A star that had been steadily burning for billions of years can, within just a few weeks, transform from a complete sphere into a diffuse stream of gas. These events provide direct evidence that spaghettification is not merely a theoretical idea. It is a real cosmic catastrophe happening throughout the universe. There is another important question. If a human spacecraft approached a black hole, would it also be spaghettified? The answer depends on the type of black hole. If the spacecraft approached a stellar mass black hole, its enormous tidal forces could tear apart the spacecraft and everything inside it before it even reached the event horizon. But if it were traveling toward a supermassive black hole at the center of a galaxy, a person could potentially cross the event horizon without immediately being torn apart. However, Once that boundary is crossed, no information can ever travel back outside. There would be no way to escape. Many science fiction stories love portraying people traveling through black holes to explore other dimensions or alternate worlds, deliberately downplaying the destruction caused by extreme gravity. But the real universe is far more brutal. A black hole gives matter no easy opportunity to approach. Long before reaching the black hole's core, tidal forces can tear apart everything: solid, liquid, and gaseous matter. Planets and stars can be broken into thin streams of particles. Eventually, an entire celestial body can become nothing more than a glowing stream of material inside an accretion disk. We look up at the night sky and see a peaceful river of stars. But it is difficult to imagine that deep in space, scenes of unimaginable destruction are constantly taking place. Black holes remain hidden in darkness. We cannot see or touch them directly, yet through extreme differences in gravity, they possess the power to tear celestial bodies apart. Spaghettification is only one of the terrifying abilities of black holes. Across the vast universe, countless other strange and extreme celestial objects remain hidden in the darkness, waiting for us to discover them. Among the countless objects in the universe, neutron stars are already among the densest and most terrifying celestial bodies known to science. But magnetars are the most extreme and violent objects among neutron stars. They are the remnants of massive stars that died and collapsed, compressing their cores to unimaginable densities. Their masses can exceed that of the Sun, while their diameters are only about the size of a small city. Extreme compression, incredibly rapid rotation, and enormous stored energy allow magnetars to generate some of the most powerful magnetic fields in the universe. To understand how terrifying this is, compare it with Earth. Earth's magnetic field is strong enough to help protect our atmosphere and support life. Then consider the powerful magnetic fields used in MRI machines, among the strongest magnetic fields humans can routinely create. A magnetar's magnetic field can be hundreds of billions of times stronger than Earth's magnetic field. Compared with an MRI machine, the difference can reach enormous orders of magnitude as well. At this scale, we are no longer talking about a simple difference in strength. It is an entirely different level of physical violence. One of the most mind-blowing facts is that a magnetar's magnetic field can directly affect the structure of matter. On Earth, atoms are stable. Molecules, cells, and physical objects can maintain their normal structures. But near a magnetar, the magnetic field can become so powerful that it distorts electron clouds and atomic structures. Chemical bonds can be disrupted, and matter can be forced into highly unusual configurations. Under sufficiently extreme conditions, solid objects, liquids, gases, metals, rocks, and biological structures could be severely affected. Many people assume that terrifying celestial objects rely on temperature, gravity, or explosions. A magnetar does not need to physically touch you. Its extreme magnetic field and radiation can severely disrupt matter, electronics, and biological systems at sufficiently close distances. If a magnetar appeared near the edge of the solar system, it would not need to approach Earth directly. Electronic systems across the planet could be catastrophically disrupted. The atmosphere could be disturbed. Earth's magnetic environment could be severely affected, and the consequences for global ecosystems and human civilization could be devastating. The birth of a magnetar also explains why it is naturally so violent. When a massive star runs out of fuel late in its life, it can no longer resist its own gravity. Its core collapses rapidly while the outer layers fall inward. The star's original magnetic field becomes enormously amplified as the core is compressed, while its rotation speeds up dramatically. A newborn magnetar can rotate hundreds of times per second. Its rapid rotation combined with its immense magnetic field creates a violent region of high-energy radiation around the star, turning the surrounding space into a cosmic danger zone. And magnetars are not always stable. Their crusts can suddenly undergo enormous starquakes. The surface can fracture in an instant, releasing tremendous amounts of energy. In just a few seconds, a powerful magnetar flare can release an enormous amount of energy, comparable to the sun's radiation over a very long period. A single giant flare can affect enormous regions of surrounding space, blasting away or ionizing gas and dust. Nearby clouds and matter can be devastated by the intense radiation. Even more frightening is the magnetar's small size and ability to remain relatively hidden. Unlike a supernova, it does not always shine brilliantly across an entire galaxy. And unlike a black hole, it does not necessarily have a huge, obvious accretion disk. Many magnetars can remain quietly hidden in the darkness of deep space. That makes them difficult to detect and predict. They are like invisible killers deep within the universe, silently waiting before unleashing devastating magnetic storms. Imagine a spacecraft approaching a magnetar. Before it even encounters extreme heat or overwhelming gravity, the spacecraft's metal structures could be severely affected by the magnetic field. Its electronic instruments could fail, precision equipment could be damaged, and its systems could collapse. Forget landing on a magnetar. Even observing one from relatively close range would expose a spacecraft to enormous radiation hazards. That is one reason humanity cannot simply approach and study magnetars up close. The terror of a black hole is destruction through gravity. The terror of a magnetar is destruction through extreme magnetic fields and radiation. A black hole can consume planetary material and leave much of it orbiting in an accretion disk. A magnetar's magnetic environment can severely disrupt matter at the atomic level. It represents some of the most extreme physical violence produced by stellar evolution. The universe is far more dangerous than we imagine. About 50 light-years from Earth, in the constellation of Centaurus, astronomers studied a bizarre celestial object that challenged our understanding of stellar remnants. It is BPM 37093, a white dwarf famously nicknamed the Diamond Star. It is one of the best-known candidates for a white dwarf with a crystallized, carbon-rich interior. Many people have heard its name, but few realize how extraordinary this object really is. The white dwarf is roughly 4,000 kilometers across, while its mass is far greater than Earth's. Much of its interior is believed to consist of highly crystallized carbon. In simple terms, it is like an enormous cosmic diamond. To put its scale into perspective, natural diamonds on Earth are usually tiny crystals. Even a 1-carat diamond can be extremely valuable. But the amount of crystallized carbon inside this white dwarf is unimaginably large. If it could somehow be brought to Earth and valued like ordinary diamonds, the number would be beyond comprehension. Yet, despite being filled with what sounds like unimaginable treasure, this object would be one of the most barren and desolate places imaginable. There is no life, no color, only extreme cold and darkness. To understand how such an object formed, we first need to understand how stars die. This object was once a normal star, far more massive than Earth. It once produced light and heat and possessed its own stellar system. Like other stars, it remained stable because nuclear fusion inside its core released enormous amounts of energy. But when a star reaches the end of its life and its nuclear fuel is exhausted, fusion eventually slows down. The outward pressure supporting the star weakens, and gravity causes the star to contract. Because this particular star was not massive enough to collapse into a neutron star or black hole, it eventually expelled its outer layers and left behind an extremely dense core. It became a white dwarf. What makes this white dwarf especially interesting is its carbon-rich core. During the star's evolution, enormous pressure and temperature developed inside it. Over billions of years, extreme compression caused the carbon within the interior to crystallize into a stable, solid structure. In other words, deep inside this dead star lies an enormous crystal, like carbon core. About 750 light-years from Earth, in the direction of Leo, astronomers discovered one of the darkest exoplanets ever observed. It is known as TRES 2b. Since its discovery, it has challenged our understanding of planetary darkness and became widely recognized as one of the darkest known planets. Many people think of black as simply the background color of empty space, but the darkness of this planet belongs to the planet itself. It is truly almost completely black. Its darkness is far deeper than coal or asphalt, and can appear darker than the surrounding cosmic background. It is a genuine dark world. The numbers make its strange nature easier to understand. Earth has an albedo of roughly 0.3, meaning it reflects a significant fraction of the sunlight it receives. That is why we can clearly see Earth from space. Jupiter and Saturn also reflect substantial amounts of sunlight and appear bright when illuminated by the sun. But TRES 2b reflects less than 1% of the light that reaches it. That means almost all incoming visible light is absorbed rather than reflected. Only an incredibly tiny amount of light escapes, making its silhouette extremely difficult to detect directly. Many people wonder if a black hole absorbs light through its immense gravity, and this planet has neither extreme gravity nor the ability to trap light. How can it be so dark? The answer is that its exact darkness is not completely understood. However, its extremely hot atmosphere and lack of reflective clouds are thought to play an important role. It is a type of hot Jupiter, a gas giant much larger than Earth and extremely close to its host star. Its orbital period is only a little more than 2 days. Because of its extremely close orbit, the planet is constantly blasted by intense stellar radiation. Its atmosphere reaches temperatures of more than 1,000 degrees Celsius. The extreme heat changes the chemistry of its atmosphere. Under such intense heating, ordinary reflective clouds cannot easily form. Instead, unusual atmospheric chemistry allows materials that absorb visible light to dominate. The result is an atmosphere that absorbs almost all incoming starlight, leaving very little light to reflect back into space. In simple terms, the outer atmosphere acts like a natural superdark absorbing layer. And the strangest part is that its extreme darkness does not mean the planet is cold or lifeless. Because it remains so close to its star, it is constantly heated. Its atmosphere stays extremely hot and active. Powerful atmospheric circulation continuously moves material around the planet, helping maintain its unusual light-absorbing properties. This allows the planet to remain incredibly dark over immense periods of time. Yet this pitch-black world also contains one of the most beautiful contrasts in the universe. Although the planet itself is almost completely black, its extreme temperature causes its atmosphere to emit a faint reddish glow. Along the edge of the dark planet, a subtle reddish or pinkish light can appear. It looks like a black ghost floating through deep space, wrapped in a thin veil of blood-red light. Strange, terrifying, and beautiful at the same time. This unique appearance makes it one of the most unusual worlds known to astronomy. Continued observations have shown that the existence of such a dark planet challenges our assumptions about how planets reflect light. We once assumed that planets would always reflect at least some noticeable amount of light. But Trace 2b demonstrates that planetary atmospheres and environments can produce incredibly unusual optical properties. A planet's brightness does not simply depend on its size. It depends on its atmospheric composition, orbital environment, temperature, and many other factors. This planet also has an extremely hostile environment. Its close orbit creates powerful tidal effects. It is likely tidally locked, meaning one side remains facing its host star. One hemisphere experiences relentless stellar heating, while the opposite side faces the darkness of space. The temperature difference between the two sides can be extreme. Its atmosphere is constantly moving through violent winds, turbulence, and enormous temperature gradients. There is no stable environment suitable for life. Many people look at the night sky and see something bright and beautiful. But the universe also contains countless hidden dark worlds. They emit little or no visible light and can be incredibly difficult to detect. This black planet is one of the clearest examples. It does not possess the gravitational violence of a black hole or the magnetic power of a magnetar. Instead, it became extraordinary through its almost complete darkness. In traditional astronomy, planets are generally defined as bodies that orbit stars. But as deep space observation technology improves, astronomers have discovered enormous numbers of objects that challenge this simple picture. They can have masses, sizes, and structures consistent with planets, yet they do not orbit any star. Instead, they drift alone through the vast, freezing emptiness between stars. These are rogue planets, also known as free-floating planets. Compared with ordinary planets protected by a host star, rogue planets have an incredibly harsh fate. Their skies are permanently dark. There are no sunrises, no sunsets, no normal day-night cycle. They receive little or no direct heat from a star, so their surfaces can remain at temperatures far below freezing. Their worlds can become frozen, silent, and almost completely lifeless. If other planets are members of a cosmic family, rogue planets are like cosmic orphans, worlds thrown out of their homes and left to wander alone. Many people wonder, are these planets born as wanderers? Not necessarily. Many of them were originally born inside normal planetary systems, just like Earth. They once had stable orbits around their stars. But during the chaotic early stages of planetary system evolution, some were violently thrown out of their home systems. In the early solar system, conditions were relatively stable compared with some other systems. But many young planetary systems contain numerous planets and smaller bodies interacting through gravity. Orbits can cross. Planets can collide. Large planets can gravitationally disturb smaller ones. If a planet receives enough of a gravitational kick, its orbit can be altered so dramatically that it escapes the gravitational control of its host star. It is then thrown into dark interstellar space and begins an endless wandering journey. Some planets may also become unbound when their host star evolves, loses mass, or dies, changing the gravitational structure of the entire system. Eventually, the planet can drift away. The most astonishing part is the possible number of rogue planets in the Milky Way. Astronomical estimates suggest that there could be hundreds of billions of free-floating planets in our galaxy. That means there may be enormous numbers of lonely worlds traveling through the spaces between stars. They emit little light, reflect almost none, and often lack obvious radiation signatures, making them extremely difficult for humans to detect. They silently hide in regions of space we cannot easily see. Many people assume that without starlight and heat, such planets must be completely frozen and lifeless. But scientific research has challenged that assumption. Some larger rogue planets may have active geological interiors. Their cores could continue producing heat. Deep beneath thick layers of ice, liquid oceans might potentially survive, protected by geothermal energy and layers of insulating ice. This means that even on a world trapped in eternal darkness, there could theoretically be environments capable of supporting unusual forms of life. Such life would completely challenge the logic of life on Earth. Earth's surface ecosystems depend heavily on sunlight. But hypothetical life beneath a rogue planet's ice could instead depend on energy from the planet's interior. It could exist its entire life without ever seeing a star. If such life really exists, its entire understanding of the universe would be different. Its world would have been born in darkness and would remain dark forever. It might never know what sunlight or a bright sky looks like. Some planets may also become unbound when their host star evolves, loses mass, or dies, changing the gravitational structure of the entire system. Eventually, the planet can drift away. The most astonishing part is the possible number of rogue planets in the Milky Way. Astronomical estimates suggest that there could be hundreds of billions of free-floating planets in our galaxy. That means there may be enormous numbers of lonely worlds traveling through the spaces between stars. They emit little light, reflect almost none, and often lack obvious radiation signatures, making them extremely difficult for humans to detect. They silently hide in regions of space we cannot easily see. Many people assume that without starlight and heat, such planets must be completely frozen and lifeless. But scientific research has challenged that assumption. Some larger rogue planets may have active geological interiors. Their cores could continue producing heat. Deep beneath thick layers of ice, liquid oceans might potentially survive, protected by geothermal energy and layers of insulating ice. This means that even on a world trapped in eternal darkness, there could theoretically be environments capable of supporting unusual forms of life. Such life would completely challenge the logic of life on Earth. Earth's surface ecosystems depend heavily on sunlight. But hypothetical life beneath a rogue planet's ice could instead depend on energy from the planet's interior. It could exist its entire life without ever seeing a star. If such life really exists, its entire understanding of the universe would be different. Its world would have been born in darkness and would remain dark forever. It might never know what sunlight or a bright sky looks like. That is one of the most fascinating possibilities in the universe. Rogue planets are also among the safest and most dangerous objects in space. They can be safe because they are no longer tightly bound to a stellar system and may avoid events such as stellar eruptions or certain orbital disturbances. But they can also be dangerous. Because they travel freely through interstellar space, a rogue planet passing through another planetary system could disturb planetary orbits. It could trigger gravitational chaos and potentially cause collisions between celestial bodies. In the right circumstances, such an encounter could create a catastrophic disturbance for an entire planetary system. Compared with the violence of black holes, the magnetic terror of magnetars, and the strange darkness of black planets, the horror of rogue planets lies in their extreme isolation and mystery. They may have witnessed the birth and flourishing of their original planetary system. They may have experienced violent gravitational chaos and been expelled from their homes. Now they remain trapped in the darkness, wandering through space for billions of years with no destination and no home. The universe has never been only about warmth and beauty. It also contains countless forgotten corners. Rogue planets are victims of cosmic instability and perhaps the loneliest travelers in the universe. Their endless journeys remind us of one of the universe's harshest truths. Not every planet gets a stable home. Not every world gets light. The mystery and brutality of the universe will always exceed human imagination. In the vast universe, every star has its own life cycle. They are born from clouds of gas and dust, begin shining and producing heat, and eventually face death. The endings of low and medium-mass stars are relatively peaceful. They slowly shed their outer layers and quietly evolve into white dwarfs, fading into the depths of space. But the deaths of massive stars are dramatically different. Their lives can end in an enormous, spectacular explosion. This is a supernova, one of the most extreme destructive events in the universe. To understand how terrifying it is, let's use numbers. The Sun, the center of our solar system, has continuously released light and heat for billions of years. But a supernova can release an enormous amount of energy in an extremely short period, briefly becoming one of the brightest events in a galaxy. That immense energy is released over a very short time. The explosion produces an extraordinary amount of light that can shine across enormous distances. For a brief period, a supernova can become one of the brightest sources in an entire galaxy. Even in the deepest darkness of space, such an explosion can be visible across enormous distances. Supernova explosions follow specific stellar rules. One major pathway occurs when a massive star, typically more than about 8 times the mass of the Sun, reaches the end of its life. Inside these giant stars, nuclear fusion proceeds through increasingly heavy elements. Hydrogen fuses into helium, followed by heavier elements such as carbon, oxygen, and eventually silicon, ultimately producing iron group elements. When the core accumulates too much iron, the star reaches a critical limit. Iron cannot release energy through fusion in the same way lighter elements can. The source of outward pressure suddenly collapses. At that moment, the star loses its balance. The enormous mass of the outer layers begins collapsing inward under gravity at tremendous speed. Trillions of tons of stellar material crash inward toward the collapsing core. The resulting extreme compression generates a powerful rebound and shock wave. That shock wave then blasts the star's outer layers violently outward. The star tears itself apart in one of the most powerful explosions the universe can produce. But the universe has another extreme phenomenon, the cosmic void. Imagine a region so empty that almost no galaxies, stars, or other matter exist within it. Inside such a region, there would be almost no significant matter or gravitational disturbances from nearby structures. A spacecraft traveling through it could experience an almost unimaginable sense of isolation. The entire brilliance and activity of the universe would feel impossibly distant. There would be no nearby celestial bodies to guide or disturb its journey. A probe could continue drifting through the darkness for an incredibly long time. Yet these enormous empty regions may also contain clues about the deepest mysteries of the universe. Because they contain so little matter and relatively weak radiation, they preserve conditions that can help scientists study the large-scale structure of the cosmos. Compared with dense regions filled with complicated matter interactions and energy exchanges, cosmic voids have experienced less influence from later cosmic evolution. That makes them valuable natural laboratories for studying the origins of cosmic structure and the expansion of the universe. Astronomers around the world continue studying these enormous regions, hoping that the emptiest parts of the universe may reveal answers to some of its greatest mysteries. The Milky Way and its countless stars make us feel the enormous scale of the cosmos. But giant cosmic voids remind us that the universe is not only filled with stars. It also contains vast regions of almost nothing. These enormous empty spaces can stretch across hundreds of millions of light years. They remain among the strangest large-scale structures in the universe and continue challenging our understanding of cosmic evolution. The universe's beauty and mystery constantly push beyond the limits of human knowledge. There is another extremely strange object in the universe that astronomers once regarded as one of the greatest cosmic paradoxes. Its physical size can be surprisingly small compared with an entire galaxy, yet its brightness can overwhelm the combined light of billions of stars. An object occupying a region roughly comparable to a planetary system can produce an amount of light powerful enough to compete with an entire galaxy. Even from billions of light years away, we can still detect it. This seemingly impossible cosmic phenomenon is called a quasar. So what exactly is it? And how can something so compact produce such extraordinary amounts of light? Today, we're going to uncover the mystery of quasars. Hello everyone, I'm Space Beyond Limits. Back in the 1960s, astronomers detected an extremely strange signal while observing deep space. From an incredibly distant region of the universe came powerful radio emissions and an extraordinarily bright source of light. At first, scientists thought they had discovered an ordinary star. But after repeated observations, they realized its brightness was far too extreme. It was much brighter than any known star. Based on its size, structure, and behavior, it did not fit the characteristics of an ordinary star, galaxy, nebula, or supernova. It seemed to belong to no known category of celestial object. So scientists gave it the name quasar, short for a quasi-stellar object, something that looks star-like but is not actually a star. Its numbers completely changed our understanding of cosmic physics. Our Milky Way contains hundreds of billions of stars. The combined light of countless stars, nebulae, and other objects creates the galaxy we see. Yet a quasar's central source can be confined to a region much smaller than an entire galaxy. Compared with the Milky Way, its size is almost insignificant, and yet its luminosity can reach thousands of times that of the Milky Way. Its immense brightness can travel across billions of light years, passing through layers of interstellar dust and gas before finally reaching Earth. Even more astonishing is the fact that quasars are extremely distant. Many are found billions of light years away. Under normal circumstances, light from such distant objects should become increasingly faint and difficult to detect. But quasars are the opposite. Even from the deepest regions of the observable universe, they can remain among the brightest objects we can detect. For a long time, astronomers had no idea how something so compact could continuously produce such enormous amounts of energy. It became one of the most difficult astronomical mysteries. The answer lies at the center of galaxies. When a supermassive black hole rapidly accretes enormous amounts of surrounding gas, stars, and other matter, that material begins spiraling inward. As the matter falls toward the black hole, it forms an enormous, extremely hot accretion disk. Inside this disk, material moves at incredible speeds. Collisions and friction heat the gas to enormous temperatures, producing powerful X-rays, ultraviolet radiation, and visible light. The result is an extraordinary energy output from a relatively compact region around the black hole. That is the true nature of a quasar. A quasar is not a star producing its own light. It is the spectacular energy-generating environment created when a supermassive black hole actively consumes surrounding matter. It represents one of the youngest, most violent, and most active stages of a galaxy. When ancient galaxies were still young, their central black holes had enormous amounts of material available to consume. The accretion process could become incredibly intense. Matter was constantly falling inward, producing huge amounts of radiation and creating the unbelievable brightness of quasars. But as time passed, the surrounding supply of material became depleted. The black hole gradually became quieter. The quasar faded, and the galaxy entered a more stable stage of evolution. This also explains why so many quasars we observe are extremely far away. Because light travels at a finite speed, when we look billions of light years into space, we are seeing the universe as it existed billions of years ago. Those distant quasars are therefore snapshots of young galaxies from the early universe. They preserve evidence of the violent conditions that existed during the early stages of galaxy formation. Meanwhile, the mature galaxies closer to us generally have much quieter central black holes and no longer produce the enormous brightness associated with quasars. Quasars therefore provide important clues about how galaxies evolve. They show that galaxies can grow through violent periods of intense activity before gradually settling into quieter and more stable states. Every peaceful galaxy may have passed through an earlier period of spectacular activity. Even our seemingly calm Milky Way may have experienced a much more active phase billions of years ago, when its central black hole could have been far more energetic. Quasars are also natural cosmic lighthouses. Because they are incredibly bright and their radiation can travel across vast distances, astronomers can use quasar light to study the material between galaxies. As quasar light travels through space, it passes through interstellar gas, dust, and other structures. By analyzing how the light is absorbed, scattered, or altered, scientists can map the distribution of matter across enormous distances. This allows us to reconstruct parts of the early universe and study structures billions of light years away. A tiny central region can therefore illuminate the history of an entire galaxy. At first glance, quasars seem to violate our intuition about how much light such a compact object should produce. But they are actually the ultimate result of gravity, black holes, and matter colliding at extreme speeds.